Compare mass of students. You have a class where this guy already mounted it, where a group of 100 students sat statistics exam and mathematics exam. And let's say the results correlate in such a way. In other ways, any increase in maths is associated with the increase in marks in statistics. So increase to that level associated with increase to that level. But this does not mean that statistics is causing mathematics. Neither is the change in mathematics causing change in statistics. No, it's only saying the two variables are related. Change in one variable is associated with change in another variable. Okay? That's when you are trying to interpret the results of correlation coefficients, don't interpret them in terms of causation. They're just talking about association. Are we together? My example actually is a good example because performance in mathematics does not cause performance in statistics. But the ability for a student to solve mathematical problems helps that student to achieve high in mathematics, right? And the same ability of solving mathematical skills helps the student to achieve high in statistics. So it's not these two variables causing it. There is a third variable which is causing both this and that. So correlation should never be interpreted as causation. Okay? That's what I'm saying there. I forgot how to switch on this. In fact, I don't see where I left it last time. That's why I'm not using my slides here. That means we need to. So that's one important aspect when looking at the correlation. Another aspect which I would want to talk about is that when you are planning to conduct correlation studies, you need to be careful when sampling, when coming up with a sample for your correlation. Let's assume These things are not helpful at all. Let's assume that you have a correlation situation, math and statistics. And the scatter plot looks like that for all the students who are doing mathematics and statistics. But if you decided to sample from these students, and then let's say in your sampling, you only sampled these students and you did the correlation study. If you compute a scatter plot of these students, would it show that there is any relationship? No. It seems as if there is no relationship. But when you look at the whole population, there is a relationship. And this is happening because you have restricted your sample to only one area. It's not a representative sample. If the sample represents high scholars and low scholars, it will show there is a relationship. Okay? So when you are sampling in studies where you know that you are going to do correlation, you have to be very careful. Make sure you are coming up with a very representative sample. Are we making sense? What I'm showing here is also true if in your sampling you only picked people who are within this range. That will be showing that there is a very, very strong relationship because you have left out those who are variating from the mean line, like these guys here. So in both cases, you will not give us the appropriate results. The results will be giving wrong information. Are you following? Is it making sense? When you are sampling, you should make sure that the sample you come up with represents people who are falling away from the mean line, represents the high scholars, low scholars, and so that you can come up with an appropriate estimation of the correlation coefficient. Okay? Otherwise, you shouldn't restrict the range of that correlation coefficient. Okay? Questions? What is the effect of restricting the range of correlation coefficient? Simukufunsa mafunso nde ine ndikafunsaso ungokhalanso chete zikutanthauza chani. Let me try to get the switch of this thing. It's a dead one. Yeah? Is that one? Yeah, it's not connected. The connection is for it. Oh, what's okay? Ah, okay. All right. Yes. Good. Ooh. So we're going to accuse the equipment when it is not the equipment. If if you have a situation where your variables are measured in ordinal measure, you remember ordinal measures? Eh? Oh, tinakambira no. Wandikanira? Tinakambira nafe. Yeah, measuring scale. When we talk about the ordinal scale, what do we mean? Any attempt? Yeah. When the scores are converted into ranks, which are now ordered. For example, somebody got 90, the other one 88, 87, 86, and then say 1, 2, 3. If you convert them into such ranks or such an ordinal measure, then you cannot use product moment correlation coefficient, because that will not give you the right measures. Oh, why? Hey, if you have the two variables all measured in ordinal scale, then the right correlation coefficient you should use is called the rank correlation coefficient. And the rank correlation coefficient is also called Spearman rho. Rank correlation coefficient. Oh, anakuza ari muri nsonga muno. Anati muri nsonga muno. Azalongoswa iko asakuzozeni zisiyeni feti zimwatiyo. So rank correlation coefficient is used when you have all the scores measured in ordinal scale. Let's say, for example, statistics is ordered from number 1, 2, 3, 4, depending on their performance. Mathematics ordered 1, 2, 3, 4, depending on their performance. Then you use ordinal rank correlation coefficient, which is also referred to as Spearman rho. Actually, if you're checking on a computer, it will be Spearman rho. You want to say rank correlation coefficient. Spearman rho. Spearman because the person who came up with the formula for computing rank correlation coefficient is a guy by the name of Spearman. Just like when we're talking about product moment correlation coefficient, we said Pearson R, right? Because the guy who came up with the formula is a guy by the name of Pearson, Carl Pearson. And the formula used for computing Spearman rho is like that. That's Spearman rho equals 6 sum of d squared divided by n in brackets n minus 1 n squared minus 1. That's the formula. 6 sum of d squared divided by n times n squared minus 1. Any idea as to what those things are talking about there? Any guesses? I'm still not convinced why this thing is not working. What is the N? Number of, yeah. And in this case, it's not number of scores, it's pairs of scores, right? Mathematics, statistics. So the only thing which is not known here is D. D stands for differences. Differences between ranks. That's the D. Let's take a simple example. Yes, now behave. Race. No signal. Where? Istanbul, you are the dissolve of these things. What is the problem now? Mwakopera phone ahead? Okay. Let's assume that we had scores for students 3, 4, 5, 6, 7. Let's assume that these numbers are positions of students because this is student. And so this is where end up. This student scored 90 in maths. This one 88, 86, 79, 70, 75, 74, 60. So you have ranked them into number 1, number 2, number 3, number 4. So this is an ordinal scale. Okay? What type of scale is this? Yeah, this one is an ordinal scale. But this is also a scale, right? What type of scale is this? A ratio, okay. Let's assume that these same students did the statistics, right? Statistics, and this one got a 77, this one 80, this one 75, 90, 69, 58. Okay, 77. Okay. Let's for argument's sake put this one to 76 since there is that one there. Okay. Now, in terms of ranking these students in positions, how do they rank be? Who is number 1? This one, Ed. Number 2, this one. Number 3, this one. Number 4, this one. Oh, okay. 5, 8. And this one is 6. This one is 7. You see how the ranks have differed now, eh? So the D in that formula is going to be equal to 1 minus 3. 1 minus 3 is equal to this d8. Okay, I'll put it like that, which is equal to minus 12. 2 minus 2, 0. 0. 3 minus 5. 3 minus 5, which is equal to minus 2. 4 minus 1, which is equal to, so 4 minus 1 equals 3. 5 minus 6 minus 1. 6 minus 7. 7 minus 4. 3. Okay. Minus 2 plus 0. Minus 2 plus 2. Oh, this is minus 12. So minus 4, Minus 3, minus 7, Minus what, Yeah. Minus 8. Minus 9. Yeah. This is where this is minus 1, minus 2, minus 4, plus 3. So it is minus 1, 8. Minus 1, 0. Oh, minus 2 here. We are adding. So we are saying minus 2 plus 0 is minus 2, 8. Plus minus 2. No. Minus 4. Okay. Plus 3. Minus 1. Minus 1. Minus 1 minus 2, Minus 3, right? Plus 3, 0. Okay. The rule there should be always the answer is 0 if you try to sum them. Wait. You remember that rule, We made it somewhere when we were doing deviation scores. You remember? So these negative deviation scores plus and positive deviation scores should add up to 0. So similarly here, it's also deviation which we are dealing here. So they should add up to 0. So since in that formula, we are doing a summation 8, 6 sum of, what did I show it very well? I think I made a mistake when I was making the formula 8. It said P equals, should be 1 minus 6 sum of D squared, over n squared minus 1. Did I show this one here? I made a mistake here. Make a correction. So, if we were to add these d's directly, we'll get 0 here. That's why the d's are what? Being squared. The following, is not. So I'll cure him on an exam. So we are saying that if you add these deviation scores, they always add to 0. And that's why, to avoid that problem, you square them. So you must have d squared here. Okay? So minus 2 times minus 2, 4. 0 times 0, 0. Minus 2 times minus 2, 4. 3 times 3, 9. Minus 1 times minus 1. Minus 1 times minus 1. 3 times 3, 9. Okay? So now you have got a sum of, if you add this, it will be sum of d squared. Just addition of those. 4 plus 4, 8, plus 9, 17, 18, 19, 28. Umeona? Yes, already. So what we are saying here, it would be equal to 1 minus 6 times 28 divided by, what is n in this? 7 times n minus 1 equals 6. 6 times 6. Yo. Yeah. Yes, that's why it's in brackets here. Oh, okay. No. You're right. You're right. 7 times 7 minus 1. So it should be 48. Thanks for that. Yes. So if you compute that, it should be able to give you the correlation coefficient. 6 times 28 is equal to what? You don't have the calculators. Yeah. 168. 7 times 48. 336, which is equal to, so it is 1 minus this 168 divided by 336. Divided by 336. 0.5, yeah? Oh. Which is equal to 1 minus 0.5 is equal to 0.58. Yeah. So this is your correlation coefficient. You have figured it? Yeah. Spearman law. So, oh. I asked you to compute a rank correlation coefficient on the assignment. Oh, yeah. And that's why I'm showing you how to do it. Is there any problem on how to do this? From the way I've shown you? No problem, right? Kapangeni kaya. Whatever, ikavuta. Sikavuta. What I've not, when we were doing product moment correlation coefficient, were you there? When we were doing the computations? That one is much more complicated than this one. And complicated because you remember how to come up with standard scores. You must first compute a mean, and then from the mean you should also compute a standard deviation. Then you should subtract the mean from every score. Uh, uh, and for you to be to be able to come to subtract the mean from every score, convert those to standard scores, and all those things, right? Which was a very, very long process. Even that process is not really complicated. It's just long and tedious. This one is much, much shorter. And that's why this one I said, let them practice. Because ideally, you should be able to do that. You should be able to do this. In terms of interpreting the correlation coefficient, it is no different from the way you interpret it for product moment correlation coefficient. You remember what we said, that the correlation coefficient must range from 1 to 0 to -1, right? The closer it is to 1, it means that there's a very strong correlation, positive, right? The closer it gets to 0, it's a weak correlation but positive. On the negative side again, the closer it gets to -1, very strong but negative correlation. The closer it gets to 0, weak but negative correlation. That's what we talked about in terms of interpreting the correlation coefficient. And today, I've just gone further to say whether you get a strong, very strong, or perfect correlation coefficient. But correlation does not mean it does not mean change in one set of scores is causing change in another set of scores. When we use the word cause, what do we mean? It's not making the other scores change. If there is a change in by 1% in mathematics, that 1% is not going to make a change in statistics by 1%. It's only saying the change in mathematics is related to change in statistics. When there's a change in mathematics, you can expect the same change to occur in statistics. Okay? For example, if you look at the variables of age versus strength, the older the person gets, the stronger he becomes it. But we're not saying that age is causing strength. But that age is related to strength. Yeah, that's what I want you to understand. And even in that example of age versus strength, really it's not the aging process that makes somebody to be stronger. There are more physical changes in the body that are occurring it, making the person stronger. So the same kinds of interpretations are true when you're doing rank correlation coefficient. Okay? Questions, whether in the computations, whether in the meaning of rank correlation coefficient. When do we use the rank correlation coefficient? When both variables are ordered like this. This is a rank order. This is a rank order. And here I'm just doing it for convenience sake. Ideally, we should have used this and this to come up with a more appropriate correlation coefficient. But if we use this and this, what correlation coefficient should we use? Just going round and round to see whether we're making sense here. If we have this type of data and this type of data, what type of correlation coefficient should we use? Yeah? Yeah. Why? Because this data is ratio. This data is ratio. We are only talking about rank if we have this type of data and this type of data. Then you can talk about product moment, because product moment requires ratio data. For whatever reasons today, this has failed to work, so just turn it off. And we also saw that sometimes you have data which is measured in nominal. Remember? Like sex. 1 standing for men, 2 standing for women. It's a dichotomous variable. A dichotomy. 2 levels. When you have dichotomous variable, let's say with you want to relate it with ratio variable. Let's say, for example, you had a situation which looks like this. This one is male. This one is female. This one is female. This one is male. This one is female. This one is female. This one is male. Okay? And you want to conduct a correlation coefficient to assess whether performance in mathematics is associated with sex. For example, if there was a question to say, who perform better in mathematics between male and female students? then that question is asking for an association between performance and sex ed. Then you would use another correlation coefficient, which is called the Bisero correlation coefficient. I think these have reached their oh, the new one is completely a ferry. What kind of a product is this? Are you going to behave in the same manner? Okay. Bissell correlation coefficient. When you are correlating ratio versus dichotomous nominal. Okay? Making sense? Nafasa project. Zovuta kale. Tika naika mo formula ngati meta pangrace mukalanga kuti zizovuta. This one I'm just saying the correlation coefficient. If you go to SPSS, you would find that if you go to correlation and then it gives you options. So it will give you R, it will give you Spearman Rho, it will give you Viscerio. Now it is you to choose where you should use R, where you should choose the Rho, or whether you should choose the Viscerio. Okay? Oh. If the two variables are all dichotomous or nominal, you can use what is referred to as tetrachoric correlation coefficient. Tetrachoric correlation, this is an O, and L. Correlation coefficient. Thus, if you were assessing whether there's a relationship between tribes of students at the University of Lilongwe and their sex, whether they are more Yao girls than boys, Yao, whether if you go to Tumbuka, it will be more Tumbuka boys than Tumbuka girls, or whether if you went to Senas among the students at the University of Lilongwe, there is also some kind of association between gender and tribe. Then you could use this. Of course, the normal tradition these days, people don't use these two. they instead use the chi-square test. Okay. For your colleagues, when I was talking to them, I was saying, I want to show them their formula. You have to read the formula one of the days. So talk about it. If we don't talk about it now, we are going to meet again one day and we'll talk about it. Okay? Questions? Okay? If the question was on an exam, in what situation would you need to use chi-square test? Will you be able to respond? Or will you say, it's not fair? Yeah. Yeah. Can I call you later? I'm in class. Will you be able to respond to my question? Under what situations would you be required to use chi-square tests? Under what situations would you be required to use the rank correlation coefficient, Spearman rule? Under what situations would you be required to use the product moment correlation coefficient? That would not be a problem, right?
So what if I use let's say, yes, also on that date?
On a rank, it will not rain. Yes. It will give you an answer, but it will be wrong answer. Because the Pearson product moment correction coefficient of Pearson assumes that you have ratio data. You remember the formula for Pearson, right? I'm moving this, assuming that we are able to follow, right? We copy it. The formula we had for Pearson R was the R equals sum of z x z y over n your Zx would have your, do you remember where we get Z scores? We assume that you have conducted a study and you have conducted the frequency distributions and those things, and then you find that the scores are distributed in that order. Remember that? So on Baraka, they will never show this. This can only be obtained in the ratio data. In the ratio data, it's possible for you to get one student 50%, another student 50%, another student 50%, another student 50%, and one student is 90, the other. So maybe you have 15 students who got 50%, 10 students who got 80%, 11 students who got 40%, and the like. And you can have this kind of distribution. But once you have put them number 1, 2, 3, 4, 5, you will have lost that characteristic. So having lost that characteristic, you cannot come up with z scores of x. Neither can you come up with z scores of y. Okay? So it will give you wrong data. Of course, it's not that if you enter the data in 1, 2, 3, 4 in the computer, it will not compute you elsewhere. It will compute R, but that R you will be getting will be based on wrong information and will not get the right correlation coefficient because of this. Have I answered your question? Okay. Another question. Maybe we can have some 5 minutes. Just take your legs.